Hope you're doing well. We're going to start chapter 3 today. So let me go over to our notes. Let me go all the way to the bottom. This was the review stuff, so we're going to be doing 3.1, which is basic identities. So basic identities that you already know would be cosecant is 1 over sine. You could also go the opposite way and say that sine is 1 over cosecant. We also know secant is 1 over cosine, and vice versa. Tangent is 1 over cotangent, again, or vice versa. Also, tangent and cotangent can also be written in terms of sine and cosine. So tangent is sine over cosine, and then cotangent is cosine over sine. So we still need to know all of these, and we'll get into, using them a good bit. We also know the fundamental identity, which is sine squared plus cosine squared is equal to 1. Now, I'm actually just going to show you 2 more identities that actually just come from this fundamental identity. So I'm actually going to write it over here as well, because I'm going to show you 2 new identities that we can get from this. So you can always do whatever you want to an equation as long as you do it to everything. So something we can do here is if we divide everything by cosine squared x, let's see what we get. So I get sine squared x over cosine squared x plus cosine squared over cosine squared. You'll notice I'm always bringing that x with me. You never want to lose that. So sine over cosine is tangent. So if they're both squared, then we have tangent squared. Cosine squared over cosine squared, anything over itself would just be 1. And then 1 over cosine squared, 1 over cosine is secant, so this would be secant squared. So this is actually a new identity that we can use. Then on the other side, let's say we divided everything by sine squared x. So I get sine squared over sine squared plus, cosine squared over sine squared is equal to 1 over sine squared. This one would simplify to 1 plus cotangent squared is equal to cosecant squared. And so this is another fundamental identity. The one with tangent and secant is actually a little bit more common to see, but you could see either of these. Funny enough, for those of you who are engineering and science majors, this one actually comes up again. I mean, it'll come up for sure in 240, but it also comes up in 242. So first I want to do an example. just using some of these identities and kind of showing you what, we can do with them. So this one says, given that tangent alpha is equal to -2/3 and alpha is in quadrant 4, find the values of the remaining 5 trig functions at alpha by using identities. This one is actually very similar to something that I had on test 1. So that one said to either, I can't remember if it was started with sine or cosine, but you had to use the fundamental identity to get the other one. So if it was sine, then you had to use the fundamental to get cosine, and if it was cosine, you had to use the identity to get to sine. This one starts us off with tangent though. So I'm looking for, I want to find sine of alpha, I want to find cosine of alpha, I need to find cosecant of alpha, I need to find secant of alpha, and then I'll also need cotangent of alpha. Now you can do this in different orders. So if I'm given tangent, the first thing I would probably think is, oh, I can definitely go get cotangent because I know that cotangent is just tangent flipped. So cotangent would have to be -3/2. So me personally, I'd probably get cotangent first. After that, you kind of have some decisions to make. Sometimes I'll have students think that they can go get sine or cosine from this. The issue is using identities. So we do have an identity that tangent is equal to sine over cosine. The issue here is this is saying tangent is -2/3. The problem with this is that then I'll have people say, okay, so sine must be -2 and cosine must be 3. It doesn't work. The reason is because remember that tangent is also opposite over adjacent. It doesn't give you the hypotenuse at all. So when you do this, you're not finding the hypotenuse. You're just finding the opposite and the adjacent side. So this is going to be a no. Doesn't work. But we can go to maybe our other identities. And so what we're looking for is we want an identity that involves tangent and maybe another trig function. And then that's it for the unknowns. So we would have tangent and then maybe there's one more unknown. What we can use is actually already on the screen. We can use this identity up here. So to find secant of alpha, I'm going to use tangent squared alpha plus 1 is equal to secant squared alpha. So I know what tangent is. So tangent is -2/3. So I'm going to go ahead and replace that. Be careful, it's not saying that alpha is 2 over 3, it's saying that tangent of alpha is 2 over 3. So you can replace the whole thing. Some students may also like if I write it like this first. Remember, this is the same thing as saying tangent alpha squared plus 1 equals secant alpha and then squared. And I talked about that when I first introduced the fundamental identity. So this would be negative 2 over 3 squared. And so the squared is already there, so I'm going to keep it in blue. All I did was replace tangent alpha because that's what it gave me. Then I have plus 1 is equal to secant alpha squared. Simplifying this, I get 4 over 9 plus 1, so I can write that as 9 over 9 is equal to secant alpha squared. Simplifying more, I get 13 over 9 equals secant alpha squared. Take the square root, I get square root of 13 over, if you take the square root of both of these, square root of 9 is just 3. So there we go, I found secant. Next, I would probably say let's go get, so we want to think, does secant help us get anything else? So is there maybe another trig function that has a easy relationship with secant? And so cosine is secant flipped. So if I have secant, I can get cosine as well. Now we do want to check our signs, because technically when you take a square root, it's plus or minus. Since we are in quadrant 4, secant is going to be positive in quadrant 4, and so is cosine. So it makes sense that those are positive. So now I have cotangent, I have secant, and I have cosine. At this point, I have two options. I can either use 1 plus cotangent squared alpha equals cosecant squared alpha. I can either use that identity, which is one of the fundamentals, it's this one right here, or if you want to, you could use sine squared plus cosine squared equals 1. So you could use either one at this point. Because for both of these, I would have one of these, or like both of these have two unknowns. One of them I already know, one of them I could find out. So for instance, with this one, I have cotangent, I just need cosecant. For this one, I have cosine, I just need sine. So that's why you could use either one of these. I actually like this one better. The reason is because I actually think that the simplifying is a little bit easier on it. So that's the one that I'm going to pick. So I'm having to scroll down a little bit, but I'll go back up. So remember, I can write this as cotangent alpha squared equals cosecant alpha squared. I know cotangent because I have it written over here. So I'm going to go ahead and replace it. So I get 1 plus and and I'm replacing cotangent with -3/2. Simplifying this, so this will become 9/4. So I can make this 1 a 4/4, and I get cosecant alpha squared. This gives me 13/4 equals cosecant alpha squared. I don't really want to have to scroll down more, so I'm going to come over here. Next, I take the square root of both sides. Be careful when you take a square root, it really is plus or minus. So this would be root 13/2 equals cosecant alpha. Now the sign that we pick is going to depend on the quadrant. So since we are in quadrant 4, only cosine and secant are positive there. So cosecant is going to have to be negative. And so the positive or negative depends on the quadrant. So cosecant is negative root 13/2. And then sine would be the opposite of that, so -2/√13. Something I want you to notice here in order to check yourself is remember what tangent is, right? So tangent is opposite over adjacent. So if sine is opposite over hypotenuse, my -2 is my opposite side. My root 13 is my hypotenuse. So for cosine is adjacent over hypotenuse. So my opposite side was 3. I see my hypotenuse is the same for sine and cosine. It's square root 13. So you can kind of check yourself a little bit by understanding the relationship of the triangle with the trig functions. Now, just to warn you a little bit, on my math lab, it's going to kind of prompt you to find certain trig functions in a certain order. You do not have to do it in the order that they ask you. You can do it in whatever order you want. You're a little you're a little restricted because, for instance, if you start with tangent, your only options are to either go to get cotangent or you can use the identity to get secant. Those are your only options. So it does kind of depend on what you start with, but let's say it asks you to start with secant. You may not naturally want to start with secant. Maybe you want to do cotangent. And so there can be a little variation in these. Okay, so I'm going to keep going. Next up, I'm actually just going to do some algebra review. So algebra using trig. And there's going to be some algebra review in here, but mostly we're going to be using trig as well. You'll see what I mean when I write it out. So for example 2, I'm going to say simplify by multiplying polynomials. And so for our first example, I want to start out with just like a normal algebra example. So if I ask you like x plus 4 times 2x plus, or let's do minus, 2x minus 3. Just something like this. Then for part B, I want us to do one with a trig function. So we're going to do sine x plus 2 times sine x plus 3. And then a part C, we'll do 2 cosine alpha minus 1, and that's squared. So first, for the algebra example. When you have two polynomials multiplied like this, usually you may know it as foiling. So you have to multiply this number by everything in the second polynomial, and then you have to multiply this by everything in there as well. So I'll expand this out. I get 2x squared minus 3x plus 8x minus 12. So x times 2x was 2x squared. X times negative 3 was negative 3x. 4 times 2x was 8x. And then 4 times negative 3 was negative 12. And then you want to simplify. So 2x squared plus 5x minus 12. When we add in a trig function, it's really not much different. So I'm going to do sine times everything in the second polynomial. So that'll give me sine times sine is just like saying x times x. So x times x is x squared. So sine times sine would be sine squared. Just be careful of how you write it. Because remember, me writing this is not the same thing as writing this. Those are not the same. It would only be the same if you write it in parentheses. So if you write it like this, that's okay. So just be careful. Then if I do sine times 3, that would be 3 sine x. So you're almost just treating it like a variable. Then I'll do 2 times everything. So this would be plus 2 sine x plus 6. Now this can simplify. So I have sine squared x plus 5 sine x plus 6. Now for part C, you have to be careful here. You cannot expand out that square. Like you can't distribute out that squared. So for instance, sometimes I'll get people in like an algebra class and they see this and they tell me that it's x squared plus 16. This is incorrect. Because this is saying x plus 4 times x plus 4. So you're going to miss out on a term if you distribute that squared. You're not allowed to do it. So I'm going to rewrite this. I'm going to write it as 2 cosine alpha minus 1 times 2 cosine alpha minus 1. And then I'll go ahead and expand it. So let me do that. So 2 cosine alpha times 2 cosine alpha would be 4 cosine squared alpha. 2 cosine alpha times negative 1 would be minus 2 cosine alpha. Negative 1 times 2 cosine alpha be minus 2 cosine alpha. And then lastly, negative 1 times negative 1 would be plus 1. This can simplify. 4 cosine squared alpha minus 4 cosine alpha plus 1. So that's some multiplying polynomials review. Now we're going to do some factoring review. So I'm just going to say to factor these. And I want to start off with an algebra one, just like I did for the last example. So let's see, I can start off with maybe let's do x squared sorry, I'm thinking of one, minus 5x plus 6. And of course, we'll do some with some trig functions as well. Let me do this one first. X squared minus 4. So there's two algebra ones. Then we'll do sine squared x plus sine x minus 2. And we'll do secant squared x. And it doesn't have to be x in there, you know, I could put alpha minus tangent squared alpha. So I changed this one to alpha just so that we have some experience with different ones. Now later, you're going to have to factor trig functions, but you know, it's not going to tell you to factor. So it is good to be able to recognize when we need to factor. Usually it's all about like the pattern that you're seeing. So with this one, the fact that it starts off with a squared, that should tell you I may need to factor this. It doesn't necessarily mean you have to, but maybe. But then if you see it kind of decrease in this pattern, right? So this is x squared, and then this is just x, technically to the 1. And then this one has a secret x right here, but it's to the power of 0. Everything to the power of 0 becomes 1. If you see that decreasing pattern like this, you're probably going to need to factor. So this one factors into my 2 parentheses. So I'm like backwards foiling. So 2 things that multiply to get x would be x and x. And then for the last numbers, you're looking for 2 numbers that multiply to get 6, but add to get negative 5. Because it's a positive, they need to be the same sign. And because we're trying to get to a negative 5, they're going to both be negative. So the 2 numbers that would get us here, I could either do 1 and 6. That's not going to work. I could do 2 and 3. That one will work. For my next one, we are kind of still seeing a pattern. It's just that there is no like x term here. What's really going on is that we're seeing a 0 as that middle term. So when I split this one into my parentheses, my last numbers are going to be two numbers, different signs because it's multiplying to get to a negative. So two numbers that multiply to -4 but would add to 0. And that's going to be +2 and -2. Part C. Something that I can maybe do to help you with these is we can let sine x be like a different variable if we want. So for me, I'm just going to let it be like y. Then I just have y squared plus y minus 2. And maybe that'll feel a little bit easier to factor. Now, I'd like for you to get to a point where you don't have to do that, but at least in the beginning, it may be helpful. So if I factor this with like the y's, for instance, I have y and y. It's a -2, so they're going to be opposite signs. I'm looking for two things that multiply to -2 but would add to a +1. You should pause and do it yourself. It's going to be -1, +2. Now we just have to replace the sine x back in. So this would be sine x minus 1 times sine x plus 2. So sometimes, if maybe just seeing the trig function kind of messes you up, you can always replace it with another letter temporarily. Next, we'll do part D. And so this one is actually a lot like the one above, a lot like part B. It's just that instead of a 4, we're seeing a tangent. But this is also a difference of squares. That's what part B is called, a difference of squares. So this one would be, needs more space than that. It would be secant alpha and secant alpha, opposite sides. And then to get to tangent squared, it'd be tangent and tangent. And that's it for that one. Now I want to do another type. This is factoring if the first number is not 1. So for instance, in part C, you see how there's nothing in front of the sign? It's because there's a secret 1 right there. So we're going to do somewhere, maybe we don't have that. So let's see, I'll do 2 cosine squared alpha plus 3 cosine alpha plus 1. And we'll do this one as well. I'll do 2, let's do a tangent or something. Let's do 2 tangent squared alpha minus tangent alpha and minus 1. So for these, I like to focus on a method called it's called guess method, but it's where you just kind of think it through. So for this one, I'm going to go ahead and let cosine alpha be another letter. I'll just let it be x for this one. So then I'll have 2x squared plus 3x plus 1, just to make it a little less intense. Now, there's only two numbers that can multiply together to get the number 2. It's 2 and 1. So one of these will have to be a 2x, and one of these will have to be x. Then I think about my last number. So it's a positive 1. So I know they need to be the same sign, and then the only two numbers that multiply to 1 is 1 and 1. And we said it was the same sign. If I'm adding to a positive 3, then it's going to both be positive. And we can always check this by FOILing it back out. So I would get 2x squared plus 2x plus x plus 1. And that simplifies to my original problem, so we're good. Just be careful, we do need to put cosine back in. Now, in a normal class, I really probably would not be showing this many examples, but because it's online, I get to show you a little bit extra. Part F. Again, let's go ahead and not look at tangent because that just feels like it looks harder. So I'll let tangent alpha be x. So then I get 2x squared minus x minus 1. Just make sure you pick a different variable than what was originally in the problem. So if the original problem had x, I'd maybe choose y or b or a or just something else. So if I factor this one, two numbers to get to 2x squared would be 2x and x. To get to a negative 1, one of these will have to be positive, one will have to be negative. Now I know the numbers themselves would be 1 and 1. This is where the kind of guessing comes in, because you have to figure out which one needs to be negative and which one needs to be positive. At this point, I would usually just try one out. So for instance, let's say I put my negative right here and my positive right here. If you expand this out again, you're going to get 2x squared plus 2x minus x minus 1. This does not equal what we wanted. So that wasn't the right orientation. So then I would just flip them. So I would say, okay, so it should be 2x plus 1 and then x minus 1. And then we can check that to make sure that it's right. And yes, it would get me to 2x squared minus x minus 1. But remember, put tangent back in. Now, when it comes to factoring with a not equal to 1, that's what I would, if you're looking for more help with this kind of thing, That's exactly what I would look up. I would look up factoring when a is not equal to 1. There's something called a C method. I've heard of a few other methods. That's something that I would recommend kind of looking elsewhere if you need some more help, or making like an appointment with me, and maybe I can teach you another method or something. There's one more type of example I want to do for factoring, and this is like factoring out a greatest common factor. So let me show you this one. 2x cubed plus, let's say 4x squared minus, let's just say x. I don't know. And then we'll do a trig version. This one I'm going to do, see, cotangent squared x minus cotangent x. So for g, sometimes when we factor, we can look for what's called a greatest common factor. So in this case, all of these have an x, which means I can factor it out to the front. So I'd then get 2x squared plus 4x minus 1. Now that doesn't factor any further, so we can leave it there. For part H, we can let it be a different letter if we want. So let's say, let me let cotangent x be, let's do b for this one. So I get b squared minus b. If both of these have a b, that means it can come out to the front. I can factor it out. And I'd be left with b minus 1. Replace in the cotangent. So I get cotangent x times cotangent x minus 1. So sometimes we just need to factor out like a greatest common factor. Now this was a good bit of factoring examples. I like to go through all these because often I find that students struggle with the factoring, especially later in chapter 4. So in chapter 4, there's going to be some problems where we need to factor and stuff like that. And I just think it's a good time to start reviewing those algebra skills. I'm leaving the like just algebra kind of stuff for a minute. We'll sprinkle in some more algebra as these sections go on. Chapter 3 and Chapter 4 are kind of algebra heavy. So for our next example, I want to show you how we can use identities to simplify. So for this one, let me say it like this. Using algebra and identities to simplify. So for our first one, I have tangent x over secant x. We're going to simplify that. And then part B over here, we'll do sine x plus cotangent x times cosine x. So sometimes whenever you're trying to simplify trig, stuff, it can be helpful to maybe change into sine and cosine. Just maybe see if anything can like cancel out. So for instance, tangent is equal to sine over cosine. I also know that secant is equal to 1 over cosine. So let me go ahead and write these in, and we're going to maybe see if we can cancel anything out. I want to remind you that dividing is like multiplying by the reciprocal. So let me rewrite this as sine x over cosine x divided by 1 over cosine x. You may remember it as like keep, change, flip or something like that. But it's saying instead of dividing, let's change it to a multiplication and then flip the other, like the second fraction. So this would become cosine over 1. I brought this up already in our previous sections, but it's just a good review, especially now that you're just dealing with trig functions and not like numbers. So multiplication, you can cancel out. So we can cancel out those cosines, and we're left with sine x over 1, so just sine x. And we're done. That's what it simplified to. And that's way simpler to deal with than tangent over secant. Part B, I'm going to do a very similar thing. I'm going to change cotangent into its identity. So you guys kind of think about what that is. Cotangent is cosine over sine. And then I still have this times cosine hanging out. So now I have sine x plus cosine squared x over sine x. So I combine those cosines together. Cosine times cosine is cosine squared. Now I need to combine these fractions. Usually when we combine fractions, like let's say we have 1 over 3 plus 2, now let's do 1 over 2, something like this. Usually we'd say, okay, I can multiply 3 by 2 over 2, I can multiply 2 by 3 over 3. This will make both my denominators 6, and I'll be able to put these together. That's just a little example, but that's basically what we need to do here. I need to multiply this sign by something. Remember, this is technically over 1. If something does not have a denominator, you can write it over 1. And I want to multiply it by something so that it would have the same denominator as over here. I can multiply by sine x over sine x. The reason we're allowed to do this is because when you do it at the top and bottom, remember sine x over sine x is really just 1. So we're like multiplying by 1. So it's not really doing anything. So be careful about that. Sometimes I get people just multiplying it on like one side. You got to do it both top and bottom. This will become sine squared over sine plus cosine squared over sine. And I'm keeping my x's. Sorry, I'm not saying them very well. Now I can write it as one fraction. So it'd be sine squared. Kind of losing my equal to signs here. Sine squared plus cosine squared over sine. Now, sine squared plus cosine squared should look familiar to you. It's the fundamental identity. So sine squared plus cosine squared is equal to something. It's equal to 1. So this is going to become 1 over sine, which simplifies further to cosecant. So we were able to get this one down pretty far as well. Now I want to be honest with you about just what to do if this is feeling bad. I don't know how else to say it. It's very possible that your algebra skills may not be up to par. And so what I'd really need you to do is reach out to me. So let me know if this is a big struggle for you, and maybe we can make an appointment or something like that and kind of just go over some algebra review. You can maybe look up online some extra algebra review. For these problems specifically, you may need help like dealing with fractions. So maybe looking up, how to add fractions with variables in them, or how to divide fractions with variables in them, stuff like that. Could maybe give you some review topics. And I have one more kind of topic to show you. But before I get there, I do also want to bring up that none of these of what we've done in here is like equations. So for instance, all these simplifying examples and all these factoring examples, you'll notice none of them are like equal to anything. And that's on purpose because we're not ready for that yet. That's going to be in chapter 4. But that is something that we can like look forward to. So our last little subtopic is odd and even identities. Odd and even identities. So you may remember this, you may not. There's something called even functions and odd functions. So an even function says that if you plug in a negative value of x, you'll get the same result as if you plugged in a positive value of x. So for instance, x squared. X squared is an even function. Because if you plug in like a -2 or a +2, doesn't matter, you still get 4. So that's an example of an even function. What we will find is that cosine and its reciprocal secant are even functions. So cosine x is even. Now what this means is that cosine of negative x is the same thing as cosine of x. Also, its reciprocal secant. Secant of negative x is the same as secant x. And we're going to do odd on the other side. I'm going to show you a quick little example of how this is used. Let's say we were trying to figure out cosine of negative pi over 4. Instead, usually what we would have done before is I would have said, okay, let's add 2 pi to this. And so we would have taken, okay, negative pi over 4, add 2 pi. So that would be 8 pi over 4. I'd add this together, which is 7 pi over 4. And I'd have to do all that work to replace the angle. And then I'd find out that it's in quadrant 4 and all that good stuff. With this new identity, we can say, skip all that. Just take the negative out to the front or get rid of it. Sorry, I said out to the front. That's what we're going to do for odd functions, so I said the wrong thing just there. Let me repeat that. Instead of actually adding 2 pi, we can just ignore the negative. So this is the same as cosine pi over 4. So let me repeat this. The negative in cosine will just go away, disappears. And so cosine pi over 4 is root 2 over 2. So we didn't have to use coterminal anymore. Now you still can, and that's okay. You'll get the same answer. But sometimes it will make it a little easier for us. And we'll use it sometimes when dealing with like variables in the parentheses. So we will need to use these occasionally. Now let's talk about odd functions. Odd functions say that if you plug in a negative, it's the same as if you just put a negative in front and plugged in a positive. An algebra example of this would be x cubed. So think about like if you plug in a negative 2, you would get negative 8. If you plug in a positive 2, you get positive 8. So you see how that negative like stays with it if you plug in a negative? That's what an odd function does. There's also some interesting things about symmetry for even and odd functions. I won't really get too far into that right now. That is something that you'll get further into if you take 240, those of you who are engineering and science. But what's essentially happening is that it's symmetrical about the middle for even, and it's symmetrical about the origin. So it like flips for odd. This is roughly what x cubed looks like. It actually looks a lot like tangent. Anyway, sine and tangent are odd. So here's what this means. If you have a negative in the parentheses of sine, it will come out to the front. The same thing for cosecant since it's reciprocal. Tangent as well. And its reciprocal cotangent. And again, let me show you an example of this. So, example, I'll do one with sine. Let's say we're going to do sine of, let's do negative pi over 6. So before, I would have said, okay, negative pi over 6, let's add 2 pi. So that's negative pi over 6 plus 12 pi over 6. So this would be 11 pi over 6. So we would have had to change this. We would have had to say, okay, this is the same as sine of 11 pi over 6. So then I got to go into my quadrants. I got to figure out that this is in quadrant 4. And then I got to use the fact that it's a reference angle, it's negative since it's in quadrant 4, it has a reference of pi over 6 or 30 degrees, so that's going to be 1 over 2. We would have had to do all of that previous to this section. Now instead, we can say, let's bring the negative out to the front. Sine of pi over 6. Pi over 6 is the same as 30 degrees. Sine of 30 degrees is 1 over 2. So I get negative 1 over 2. And that's a lot faster than what we had to do previously. Okay, so that is it for 3.1. Just a reminder about even and odd. Basically, all it's saying is if you have a negative in the parentheses for sine, cosecant, tangent, or cotangent, that negative pulls out to the front. If you have cosine or secant negative inside, the negative will just go away. So that's really the gist of this. And then we did a bunch of algebra and trig and algebra together and all that good stuff. So that's it for this video. I will see y'all in the next one, and I hope you have a good day.